Welcome to week 9 of Digital IC Design EE 423 at Oregon Tech. Today we will be having a little bit shorter than usual set of lectures, and it will be centered around power consumption in ICs. First we'll start out with power and energy, and then we'll go through dynamic power in digital integrated circuits and static power in IC design. So first let's go over a refresher of what power and energy are, more by a definition standpoint. So power is drawn from a voltage source that you have attached to your IC design. So basically a voltage source attached to your VDD pin, or if you have multiple different VDDs that might be at different voltages, the VDD pins of an IC chip. So we have a couple different types of power and energy. One is instantaneous power. So at any given point in time, your power at a given point in time is the current being supplied by your voltage source times the voltage value of your voltage source. So I sub t times V sub t at that particular point in time is your instantaneous power. Now your energy is the integral of your power over a certain length of time. So the length of time that we're talking about here in this case is capital T, and so you take your power value for each instant in time and integrate that power value over the period of time from 0 to capital T, number of seconds, milliseconds, microseconds in time. And then finally, your average power is taking your total energy over a given time period and dividing by the amount of time that that time period took up. So E over capital T, which of course then if we substitute in the value of E is 1 over capital T times the integral from 0 to time capital T of your power P sub T as a function of time. In this slide we go through how power is calculated in different types of circuit elements. So in the one on the top here we have a voltage source, and as I said in the previous slide, the power for a voltage source as instantaneous power is the amount of current going through that voltage source times at that instant in time times the voltage value. And if we assume the voltage value, DC value, is constant, but the current can change over time, it's just the current as a function of time times the constant voltage value VDD. Next, for a resistor, the power consumption as a function of time is V squared over R. If we go back to our basic circuits courses, it's either the voltage value across that resistance, V squared, divided by the resistance, or can also be written as the current going through the resistor, so I squared as a function of time times that resistance value. So it can be, depending on whether you know the current or the voltage, you can get your power either way. And then finally, for a capacitor, we start out saying in terms of energy, a capacitor, the energy stored in a capacitor is the integral over time of the current going through the capacitor times the voltage across the capacitor as a function of time. And then we can substitute in as our current through a capacitor is C times dV dt. So we now have the equation is the integral of C dV dt times V times dt. So we can basically, the dt's cancel out, and we now get the energy is C times the integral of V, your voltage, as a function of time, integrated as a function of time, or as a function of dV. And so integrating V as a function of dV, you get 1/2 V squared. So your overall energy is 1/2 CV squared. So whatever the voltage value is squared. So that gives us energy stored in a capacitor. So in the previous slide, I said I was talking about power, but when I got to the capacitor, I only covered the energy stored in a capacitor. And you might ask, why didn't you talk about the capacitor consuming power? And the reason is, an ideal capacitor does not actually consume power. A capacitor only stores energy. And a capacitor, the power consumption that happens when we have capacitors in an IC circuit are the amount of power that is consumed as you're trying to charge the capacitor and put energy into it. You wind up consuming some power in the transistors that are being used to charge the capacitor and the transistors that discharge the capacitor. So power does get consumed as you're charging and discharging a capacitor, but it's not by the capacitor itself if the capacitor is an ideal capacitor. So now let's look at a little bit more on charging and discharging a capacitor. So when we have, let's drawn here a inverter that's driving a capacitive load, and that's typically, like we've gone through in many previous lectures, typically that's a gate load, and it's also diffusion load of the driving transistors themselves. So we have that capacitive load. If we charge that capacitor, the energy stored in that capacitor, C sub L, as we went through in the last slide, is 1/2 C sub L times VDD squared. So whatever voltage you're charging the capacitor up to, the energy stored in it is going to be 1/2 CV squared. But if you look at the equation for the amount of energy drawn from the supply in order to charge that capacitor, that energy is the integral of I sub t times VDD integrated over time. And so when you go through that equation, it turns out that that is equal to C sub L times V squared. So the total energy drawn from the supply is CV squared, but the energy stored in the capacitor is 1/2 CV squared. So it turns out that half of the energy from the VDD supply is dissipated in the PMOS transistor as heat as you're trying to store charge in the capacitor. So half of it is dissipated in the PMOS transistor, the other half of the energy is stored in the capacitor. And then if we switch the Vin back from when we had it Vin low, we were charging the capacitor up for V out. When we just switch Vin to high, we now discharge the capacitor, and that energy in the capacitor is then dumped to ground, and that's dissipated as heat in the NMOS transistor as it's pulling the output capacitance down to ground. So the second half of the charge is dissipated as you're discharging the capacitor back down to 0 volts. And so charging up and discharging the capacitor, that full loop consumes CV squared in terms of total energy, but only half of it gets dissipated as you're charging, and the other half gets dissipated as you're discharging it. So this slide goes into much more graphical detail, showing us what happens in terms of the voltage, current, power, and energy consumption over time as you're charging and discharging a capacitor through an inverter. So this example is we have a VDD of 1 volt, a load capacitance of 150 femtofarads, and we're operating at 1 gigahertz. So first let's look at the top row is, well, now let's look at columns. So if we go to the leftmost column, we have V in and V out are the top and then the second waveform. So V in starts at 1 volt and switches from high to low down to ground. Stays there for about 0.2, maybe, yeah, 0.2 to 0.3. I think that would be nanoseconds. And then at 0.6 nanoseconds switches back from 0 to 1. And you can see the second waveform in the left, second one down from the top, is our V out. V out starts low. After V in switches from high to low, V out starts switching from low to high, gets most of the way up to 1, and then V in switches back from low to high, and V out switches back from high to low. And the curve kind of follows a little bit of a curve that's got some exponential to it in places, and a linear region in other places, depending on what region of operation we're in. So the second column from the left shows the current going through the PMOS device on top. The second from the top is the current going through the NMOS device, and then the third one is the current going through the capacitor. So let's start with the current going through the PMOS device. You can see as the input is switching from high to low, the PMOS starts turning on as you get voltage across from VDD to your VN, your VGS across your PMOS starts increasing, and so the PMOS starts turning on. Initially it's in saturation, and as the VN gets lower and lower, the amount of saturation, or the amount of drive current we have across VGS, again our gate voltage is going to 0 and our source is at VDD. So as it gets VN gets closer to 0, our VGS is getting larger, and so our saturation current goes up as VGS gets larger. At some point though, as the output voltage is charging up, our VDS starts getting smaller than our VGS, and we go from a saturation region to linear region. And you can see those are labeled there. As you go from saturation to linear, then your current peak hits its peak and starts going back down, because as V out keeps getting closer and closer to VDD, there's less and less current in the linear region, and so you can see the current is tailing off kind of at an exponential rate there, decaying toward 0 current. And then there's a little bit of short circuit current there, as when we switch back from the input switches back from ground to VDD, it turns on the NMOS device to start discharging the capacitor. So you can see the second curve from the left, and the second one down is the current going through the NMOS. It follows the same pattern of very high increase in current initially as you're in the linear region, and then once it switches over from linear or increasing in the saturation region, once it switches over from the saturation to the linear region it decays back down towards 0. And you can see right when the NMOS is first turning on, there's a little bit of a blip of short circuit current for the PMOS, because both the NMOS and PMOS are turned on at the same time, when your voltage is kind of about halfway in between VCC, VDD, and ground. And you'll see on the NMOS curve there's a little bit of a blip in the middle of the saturation region of the PMOS switching as well. Both of them are pretty small, so you don't see it very much, but that is a noticeable and measurable amount of current that you should account for. And then finally, if you go from on the third graph down, you can see the current through the capacitor initially starts at 0. As you're charging it, you go to a positive current and then it decays back down to 0. And then as you're discharging it, it goes to a negative current and then decays back up to 0. Then finally, if we look at the power consumption, the power consumption through the PMOS, it is kind of follows the curve of the current through the PMOS. So you get a big spike right where the most current is through the PMOS. Similarly, the NMOS, the second one from the top, you get a spike where the current through the NMOS is the largest. And then the current through the capacitor looks very much like the voltage, or the power through the capacitor looks very much like the current through the capacitor curve. And then finally, the power consumed by VDD, you can see there's one big spike where the PMOS is turned on, and then there's a smaller spike where the PMOS has the short circuit current, but you can see there's no spike when the NMOS is turned on. And that's because you're not consuming any power from your power supply when you're discharging the capacitor. Keep in mind, the capacitor stores charge and stores energy, but you've consumed everything that you're going to consume from the power supply when you charged up the capacitor. When you're discharging the capacitor, it doesn't require any current or any energy from the power supply anymore. And that's reflected in the last column, the one on the right hand side, where it's the energy of the capacitor and the energy consumed from the power supply. You can see when you charged up the capacitor, you consumed a bunch of power from the power supply, and that power reaches its maximum once you charge up the capacitor, and it doesn't increase anymore as you discharge the capacitor. So you consume all of your energy from the power supply in charging up the capacitor, and only half of that energy gets into the capacitor. Half of that got consumed by the PMOS device, and then you consume the rest of it when you discharge the capacitor. But the overall amount of charge that you pulled, or amount of energy that you pulled from the voltage supply, again, happened when you initially charged the capacitor. So if you didn't fully understand all of that, you can go through this slide again, but make sure that, again, this is showing how all of your energy is consumed by charging the capacitor, but half of it goes to just the PMOS device dissipation, half of it actually gets stored in the capacitor, and then you can discharge the capacitor and effectively dissipate the rest of that energy in the NMOS device when you discharge the capacitor.